Hey, so guys, before we turn these in, Kyle had a question, and maybe some of you have other questions. And because this does sort of play like homework, we could certainly answer questions before we turn them in. So Kyle's question was really good. Not that your alls aren't. But Kyle said some of my measurements were different than the ones that you had. Like, for example, on number 3, this was a measurement that you took off of a graduated cylinder. And looking at number 9, that was a measurement that you made with a ruler. And then looking at number 15, that was a mass that you found with the balance. Now, guys, if your numbers are different than my numbers, which is totally fine because measurements are always somewhat inexact, your conversion should be the same, but your answers will probably be different as well, and that's totally fine. So, is that okay? Yeah. Isaac, go ahead. Okay. Guys, anything else you want to talk about? Okay, so huck this in the basket. We'll come back and look at the calendar, and then we'll get going from there. So, guys, turn this. And by the way, guys, if you're trying to choose between turning it in late and turning it in incomplete, choose late. Do not turn this thing in incomplete.
So, because I was gone, I did all the good things.
Great, yep, yep. Just put it in the basket, y'all. Is your name on it?
Yeah.
Okay, yep. That's perfect, yeah. Here we go. All right, put this away, this away. Turn them in. Thank you, ma'am. Always. Yep. All right. So, guys, I think it would probably be a fitting time to take a look here. So let's talk a little bit about this week. Let's talk a little bit about this unit. Let's talk a little bit about the end of the quarter. So guys, the easiest way to pull this together in your head is you are now done with the quarter. So guys, if you're caught up, you are completely finished with third quarter. Obviously, we've taken all of the tests that we're going to take. The next test goes on fourth quarter's grade. It's not till fourth quarter. The homework that you turned in a couple days ago, last homework, and you just turned in your last lab and activity. So really, if you're done, you're done. But what if you're done, but there are still gaps in your grades? Well, guys, those are all due Wednesday by 2:45. This is a non-negotiable deadline. And so, guys, any homework from the current unit and then any late labs or activities that you might have, guys, please turn those in. Alex, I have not yet looked at the labs that you turned in, but other than that, guys, I've graded everything. So I don't think there was anything in the bottom of this basket other than Alex's stuff. No, it kind of ends with Alex's stuff. That's not true. James, I have a lab from you. Oh, you just turned it in. Okay. And guys, that's it. So if you're waiting expectantly for me to get something graded, that's not going to happen because I don't have it. If you turned in late homework, I am one rotation behind on recording late homework assignments. I will probably do that today while you guys are working on today's homework. So, guys, again, please watch out for Wednesday the 15th. Communicate with me as you need. And we're getting really close to being done with 3/4 of this school year, which is both amazing and a miracle all at the same time. So, guys, anything with the calendar y'all need to talk about? Are we okay? We're good? Daisy, we're okay? All right. Go ahead, McKay. No. Well, unless you're a junior. So, So, and there is a rumor out there we need to be careful of, because some of you are sophomores. Guys, many other high schools in Alpine School District are doing the Aspire test tomorrow. For the sophomores, we are not. So the only people that come to school tomorrow are the juniors to take the ACT. Sophomores and seniors have no commitments tomorrow. And then, guys, oh, what's that? Say that again. Oh my gosh, yeah, it's a big day. But you are done at noon. Go ahead. Yeah, so guys, let's talk really quickly. Most of you are juniors, so let's talk about this. What you want to do tomorrow is bring something that you can put smartwatches and phones in. Your backpack works, although the best thing to do is just leave it all at home, because you can't have any electronics in the room. What you want to do is show up about 7:30. You want a passel of pencils and a calculator with fresh batteries. You can't have food in the room. You're really coming in pretty stripped down. It's just pencils and a calculator. And then, guys, the way that this works is you'll get here about 7:30. We as teachers will open the room about 7:45, and then as soon as everybody's there, or at 8 o'clock, we'll start. So if everybody's there at 7:45, we'll just get going. Also bring photo ID. We have to pretend, well, actually that's not true. I was about to say we have to pretend we don't know you, but we can actually ID you. So if you walk into a teacher's classroom and you don't have your ID and they know you, you're fine. Otherwise, we've got to find a teacher that does know you, and it just slows things down. So bring like your school ID or your driver's license. Yeah.
I've also heard tomorrow is also an online learning day.
Well, understand, yeah. So understand. So Jessica's thought was, I also heard that tomorrow's online learning day. We like to hang that flag on things just to make us feel better about not being in school. So. Yeah, and that probably your AP classes, right? AP teachers right now are getting really desperate for time. So that's between you and your other teachers, but there won't be any obligations in this class, certainly. But your teacher should approach you on that as individuals. So James, did that answer your question? Okay, so guys, again, pencils, calculator, and photo ID. Leave everything else home if you can. And then also, guys, next Monday is a broken week as well. We have a professional development day. You know that the 12th is the end of the quarter, and every new quarter starts with a PD day. And well, not third quarter because it's Christmas. But so guys, you don't have school Monday, do you? And then we'll go from there. So other questions, calendar things? Okay, what was you just asked about tomorrow. That's right. Anything else, you guys? Are we all good? Okay, so do this. You're going to need really just calculators and note-taking materials. And guys, this goes pretty quick. This is a catch-all day. You're going to love it. Unless you don't. So guys, the date today is the 8th. The topic is on the board. The last of the new material for the unit. Guys, we should have talked about this when we looked at the calendar, but we can talk now. So guys, today's the last of the new material for the unit. All this goes on fourth quarter. When I see you Thursday, we're going to go to lab and do a lab. When I see you early next week, next Tuesday, we're going to go do another stations activity. And then, guys, the test is next Thursday. I know that things are getting hyper busy right now. Baseball, track, all sorts of obligations. Guys, so if you need to take this test, like you won't be here for the test, you're going to learn all the new material today. So technically, after today, if you're up to speed, you could take the test this afternoon. So guys, if you are going to be gone, please talk with me ahead of time. So guys, today's the 8th, and what we're doing today is molarity and intermolecular forces. Let me know when you're caught up, and we're going to get cooking. You guys okay? We good? Okay. So, guys, the first thing that's going to be important for you to understand is that this and is a hard and. These two concepts have absolutely nothing to do with each other than that they both draw on the concept of the mole. So, guys, molarity is going to be really important to us, not really this unit, but in coming units. And empirical formula is actually the lab that you're about to do. So, guys, the thing, though, that you need to understand is that as we're learning this, don't try to connect molarity with intermolecular or with empirical formulas. So, guys, we're going to do molarity. We're going to make sure you're comfortable with it. We're going to call time out, and we're really going to start over and do empirical formulas. These literally have nothing to do with each other, so don't try to connect them. So, here we go. Starting with molarity, let's define it first, and I would encourage you to scratch this down. So guys, when we talk about molarity, which is obviously based in the word moles, we're talking about solutions. And specifically what we're talking about is how concentrated a solution is. So molarity is a measure of solution concentration, and the units are moles of solute per liter of solution. So guys, you can picture the video, you can picture the salt crystal and the water molecules coming in like little tugboats and ripping the salt crystal apart. Well guys, that's solutions. But when we talk about molarity, we're talking about how much stuff is dissolved in the solution. And when we do this, we can also write this definition mathematically like this. So molarity, which is abbreviated capital italicized M, is equal to the moles of solute. And guys, remember, solute is the thing that's being dissolved, and then solution is the entire mixture when it's all put together. So guys, we're going to talk about this conceptually, then we're going to play with it mathematically, then once you're all satisfied, we're going to start over, do empirical formulas, and that's going to be our day. And some of you might even have an aha moment when we get to empirical formulas. Feel free to say out loud, aha. You guys ready to go? Okay. So, guys, let's talk a little bit about molarity. Just relax. You don't need to write anything down until the next slide. That is the wrong solute. Here we go. So, guys, this is the solute we're going to talk about today. There was some of this over in the stations activity. But, guys, this is potassium permanganate, KMNO4. And what I did is I actually made 3 KMNO4 solutions. So let me put these in order really quickly. All right, so here we go. So guys, focus on these solutions, understand the concept. So these 3 solutions are all KMN, potassium permanganate solutions, and they all have a volume of 1 liter. So 1 liter, 1 liter, 1 liter. The difference is their molarities. So guys, let's talk about this one first. This is a 1 molar solution. Here's the question. How did I make it? How do you make a 1 molar solution of KMNO4? Well, guys, let's talk. First of all, what's the volume? I already told you. It's a liter. So, guys, if the volume is 1 liter, how much KMNO4 is dissolved in here if it's 1 molar? 1 mole. So, guys, how on earth did I figure out how much of this is 1 mole? Connect to the homework you just turned in. Guys, how do we know how much is a mole? What do? Exactly, we need to find the masses. So guys, we find out that potassium is 39.1 and its Mn, manganese is 54.9, 4 oxygens is 16 times 4. I do that math, I add it up, and it's actually this much. So guys, this is 1 mole of KMNO4. So I took a liter of water, I dumped this in here, I gave it a shake, and that's a 1 molar solution. You get the idea? So guys, this is a 0.5 molar solution. Now here's the idea. If this is a 0.5 molar solution, how much stuff is in here? How much solute? Half a mole. So guys, how much more concentrated is this one than this one? This is 0.5, this is 1. So how much more concentrated is this? Twice. And you can actually see that. If I flip this over, you can actually see through the neck of the bottle because it's relatively dilute. There's not a ton of stuff in there. It's actually half this much. But then, guys, if I take the 1 molar solution, making sure this is tight, and flip that over, there's no way you can see through that. And up here, you can actually see that it's even stained the glass. Guys, this is a 1 molar solution. This is a 5 molar solution. So guys, how do you make a 5 molar solution? This times 5, liter of water, off you go. And guys, this seriously looks like grape juice. Like there's no way that you can, it's almost chunky, it's so concentrated. Yeah. That's a great question, and that's actually where we're going with this next. Guys, brilliant question. So guys, McKay's question was, is it always a liter? So let's do this. Are you okay with this 0.5, 1, and 5 relationship? Half a mole in a liter, 1 mole in a liter, 5 moles in a liter. Is that okay? Okay, so now guys, let's do this. I'm going to put the 0.5 and the 5 away, kind of, and I'm going to grab the 1 molar solution. And guys, let's answer McKay's question. So his question was, ew, that's gross. That's better. Okay, so his question was, is it always a liter? So guys, again, this is the 1 molar solution, and this stuff stains horribly, so I'm going to glove up. So guys, it's not dangerous like for your eyes, but it does stain, so I may as well try to stay clean today. All right, so guys, 1 molar solution, 1 mole in 1 liter, right? Now what I'm going to do is I'm going to pour half of it into here. All right, so now we've got half a liter of it in the beaker and half a liter of it still in the flask. Guys, here's the question. It started at 1 molar. What's its concentration now that I broke it in half? What's the concentration of this now? But hold on. How can it be 1 molar if it doesn't contain 1 mole? Because half of it's in there. Say it again, Jessica. Say it louder. It's half of both the solute and the solvent. So McKay, to your question, does it always have to be a liter? And the answer is absolutely not. But if the molarity doesn't change, the ratio needs to be the same. So we started when this was all together 1 to 1, right? But when we broke it in half, now we have 0.5 divided by 0.5, but 0.5 divided by 0.5 is still 1. So simply cutting this in half doesn't change the molarity. So guys, what about this? What about the drips that are coming off my finger? What are the molarity of those drips? Also 1 molar. So guys, again, molarity does not change simply by separating something. And you're going to see that on the test. So if we take this and if we pour it or we divide it or whatever we want to do, even drops, guys, this is 1 molar, this is 1 molar, those drops are 1 molar. The concentration is not changing simply by getting smaller portions of the solution. You get the idea? Questions on that? That's important. You're good? Go ahead, Sam.
Doesn't the chemical that was pouring in the water, doesn't that have mass? But it increase the mass making more than liters?
That's a beautiful question, and don't worry about this answer unless you're coming back for AP. Notice you're absolutely right that the solute has mass, right? And because it has mass, it does make the solution heavier. What it doesn't do is make the solution bigger, and so our denominator is liters of solution, and so it doesn't change the volume, but it does change the mass. And so in AP, we talk about another way to measure concentration, and it's not called molarity, it's called molality. And when we do molality, the denominator is actually the mass of the solution rather than the volume, and then it does change. Go ahead. What if there's a solute that doesn't dissolve? keep that idea, because we're about, McKay, you're on a roll, buddy. Yeah, that's exactly what we're about to talk about. So if it doesn't dissolve in the first place, it's not a solution, right? So if you add sand, it doesn't dissolve, so there is no molarity. But keep that in your back pocket, because we're about to talk about it. You guys okay with this idea about dividing things? Okay, so let's do this then, and this is where you want to start scratching stuff down. I wonder if my board works with gloves on. Hey, it does. So guys, the question then becomes this, and this you do want to write down. We need to talk about how then do we change the molarity of a solution. We now know that simply dividing it does not work. So guys, what can we do then to change the molarity of a solution? And let's talk about increase first. So guys, if we want to make salt water saltier, or potassium permanganate solution potassium permanganatier, what do we do to make the solution stronger? Literally, what do? Add more solute. So guys, if you want to make salt water saltier, add more salt. So literally, guys, if I were to take this and dump it in here, it would increase the concentration of the solution. So one of the things we can do is add more solute. I took off my gloves too soon. I'm going to try this with one. But guys, that's only one of the two answers. What is the other thing we can do, Isaac, to make the solution stronger? Okay, so let's talk. So Isaac is saying remove the liquid, and I know this isn't what Isaac's thinking, but watch. So guys, Isaac is saying remove the liquid. And if I do this, I'm removing liquid, but we've already established that the molarity doesn't change. So when you say that, what are you thinking? The solvent. But how do we do that? How do we physically remove the solvent without removing the solute? Say it again. Evaporate or boil. Guys, remember when we did that in that silly salt and sand lab at the very beginning of the year? And we boiled the water off of the salt water, and the water got saltier and saltier and saltier until it turned into sludge, and then eventually it all went away. So guys, the other way to do this is to evaporate or boil the solvent away, and then we're removing solvent without removing solute, and it gets saltier. All right, McKay, you ready? You got that ready to go? Guys, let's go the other way. Let's decrease concentration. Okay, you guys ready for a radical thought? If you want to make salt water less salty, what do? Add water. And there's a name for that. Watering it down. Diluting it. So guys, if you want to make a solution less concentrated, one of the things that you can do is add solvent, add water, water it down, dilute it, which is actually the technical term. But if you add solvent, then you're making it less salty. But guys, there's another way to make a solution less salty. Okay? What do? Remove the solute. But how do we do that? We did it in lab, not the last lab we did. What could we do? Guys, literally, what could we do to pick the KMNO4s out of this without removing the water? Are you making the connection? You can see the wheels turning. Guys, let's open it up to everybody. What can we do to get the KMNO4 out of this without removing the water? You did it in the last lab.
Make it reactive.
And make it form what?
Salt.
Well, it's already a salt. Make it form a precipitate. Guys, if we could add something to this that would bind up the KMNO4, as you were talking about, and turn it into a precipitate, then it would settle to the bottom, just like you did in lab, right? Then it would settle to the bottom. It's no longer dissolved in the solution, and at that point, it's less salty. Guys, that's what hot tub clarifier does. If the water inside your hot tub ever gets cloudy, you add this stuff that causes the cloudiness to precipitate, and then your filter can suck it out of the water, and it clarifies the water. In the same, I should have brought something. I'd have to figure out what would do it. But guys, we could do that here too. We could add another salt solution to this that would bind up the KMNO4, turn it into a precipitate, it settles to the bottom, then it's not dissolved, and the solution becomes less salty. You get the idea? So guys, let's include that in our notes, and then let's do some math, and then we're done. So guys, precipitation is the other thing that we can do to get the salt out of the water, making it less concentrated. So guys, you may want to just jot something next to this in your notes. This is on the test that you'll take next week, like word for word. There will just be a string of changes that you will make, and then it'll say, would this make the concentration go up or down? So if you have these concepts in mind, you should be fine on that portion of the test. So guys, any questions about the concepts of molarity? Y'all good? Okay, so let's shift gears and let's do the math, and then we can put this portion of today to rest. So guys, now we're going to use molarity mathematically. It's worth writing down that little subtitle. This says calculating molarity. So guys, when you calculate molarity, dimensional analysis, but what I want to do is give you the steps. Guys, there are 3 steps to these processes, these conversions. Step number 1 is you're going to set your goal, right? Goal, starting point, line, conversions, math, and round. Guys, you are going to set your goal at moles per liter. But guys, remember that the per means divided by. So when we say moles per liter, it's moles over liters. And this is where these complex conversions are going to become important, like the cycling question that we solved about a week ago, where we figured out how fast they were going in miles per hour. So guys, your goal is going to be moles per liter because that's molarity. Then your starting point is going to be mass over volume. And then at that point, you're going to make some conversions, and off you go. So guys, these questions get wildly redundant. They're the same every time. So let me show you an example. It says, what is the molarity of a solution created by dissolving 7.2 grams of salt in 500 milliliters of water? So guys, that's this. Just for context, this is 500 milliliters of water. This is 7.2 grams of salt. If I dump this in here and dissolve it, what's the molarity of the solution? Guys, I chose salt because we already know its mass and it's familiar. But that's the question we're asking. Dissolve that in there, what's the molarity? So guys, to figure this out, the first thing we need is a goal. So what is your goal? Step number 1, what's your goal? Moles over liters. So guys, we're going to write that down on the far right-hand side. Oh, this isn't salt. It's not table salt. It's calcium chloride. Sorry. I thought we were doing sodium chloride. It's calcium chloride. No wonder that doesn't look like sodium chloride. I was like, those chunks are too flaky. So guys, this is actually calcium chloride. Sorry. I grabbed the right stuff. I just forgot the question. So guys, our goal is moles over liters, and please be careful about how you structure this as you're problem solving, one over the other. Now guys, we need a starting point, and our starting point is mass over volume. So we have 7.2 grams of CaCl2, and our volume is 500 milliliters, so it looks like this. Now guys, at this point we make the connection. Why are we talking about these problems during this unit? And the answer is because these are moles conversions. Guys, look at what we need to do. We need to take grams, and we need to convert it into moles, and we need to take milliliters, and we need to turn it into liters. So this is why this fits into this unit, because this is simply a moles conversion problem. So guys, the first thing that we've got to do is we've got to convert grams into moles. I'm just going to do it for you. So guys, calcium is 40.1, chlorine is 35.5 twice, is 71. You add those together and you get 111.1 grams. That goes on the bottom. 1 mole goes on top. The grams cancel grams and you're left with moles. Simple one-step conversion. That should feel familiar given all of the molarity or all of the moles problems that we've done. Then guys, the last step to this is to deal with the denominator. We got to get milliliters into liters. There's 1,000 milliliters in a liter off your conversion chart. So guys, now it cancels bottom to top. So 1,000 milliliters is 1 liter. Milliliters cancel. We're left with liters, so we're done. And guys, that's always the way these conversions work. The only time good question, McCain. The only time it won't be 3 steps like that is if you're already given the volume in liters. And then it's actually easier because you don't have to do this. Sometimes it'll say 7.2 grams of calcium chloride in 3 liters of water. And then you just put 3 liters down there and the denominator's done. So they get easier, not harder. So guys, then at that point we need to do the math. So it's just 7.2. Be careful here. Don't forget the divided by 500. People tend to miss that because you're not used to a denominator in your starting point. So 7.2 divided by 500 divided by 111.1 times 1,000. And guys, I get 0.1296 molar. Yeah, well, this is where I try to be careful because turn your calculator towards me so you might be okay without them. Depending on the TI model, you may not need parentheses. But guys, it may be worth plugging the numbers. Yeah.
Which one do you start with?
Yeah, great question. So what we're going to do is, and this is up to you. I like to just work left to right because we all read that way, right? So what I like to do is I go 7.2 divided by 500. Then I'm done with that. Then I don't need to multiply by 1. Then I divide by 111.1. Now I'm done with that. And then I go to the next one times 1,000. Don't divide by 1. So I like to just work across. Some people like to go 7.2 times 1,000 divided by 500 divided by 111.1. I get lost. I do it that way, but it really doesn't matter. Either way is fine. So guys, did you all get 0.1296? Okay, now we need to round. So guys, and now we got to be careful because we have a denominator. So 7.2 is 2 significant digits. 500.0 is 4. So guys, we get 2, and then here we get 4, and this is perfect. So we round that to 2 significant digits, and that would be 0.13 molar. So guys, what that means then is if we dump this into here and get it to dissolve, we just made a 0.13 molar solution. Now guys, understand in this class, you actually won't be doing your own solution preps simply because we've got so many people and there's not enough room to do it. But guys, in AP, when you come back, you'll actually be doing this math and you'll be doing your own solution prep for the labs. Yeah. Molarity. So we're solving for molarity, but the abbreviation for molarity is the capital. It should be italicized, but yeah. So guys, questions on this? Ryan, you okay? Just stretching? Yeah. We good? Okay, so guys, one more to look at, and then we're going to do empirical formulas and be done. So guys, the next thing that you need to be able to do is use molarity as a conversion. Using molarity as a conversion. Again, let me show you an example of what we're talking about. So guys, the question that we're solving now is this. This is actually oven cleaner. Oven cleaner is just sodium hydroxide. But instead of buying this at Walmart, I actually made my own. So the question is this, because again, oven cleaner is just sodium hydroxide solution. But guys, this is 225 milliliters of oven cleaner. And oven cleaner is about 0.1 molar sodium hydroxide. So guys, this is it. This is 225 milliliters of 0.1 molar sodium hydroxide. Here's the question. How much sodium hydroxide, because it comes in pellets. Guys, how much sodium hydroxide is dissolved in there? Do you see the question? Let's solve it. So guys, this just becomes like regular old ordinary dimensional analysis. So step number 1 is a goal. What are we solving for? How many grams? So that's our goal, grams of sodium hydroxide. Now guys, next thing we need is our starting point. Now we've got a problem because we've got 2 pieces of information. We've got a volume and we've got a molarity. Which one do we start with? Never the molarity. Guys, you will never start, you may want to write that down somewhere next to these. Never start with molarity, ever. You will never start with molarity, you guys. So we're going to start with the 225 milliliters. Then we draw a line, and then we're ready to go. So guys, this is an interesting question. How on earth are we going to convert milliliters into grams? How are we going to get milliliters of solution into grams of sodium hydroxide? Thoughts? How can we get there? Milliliters to grams. Go ahead, Sam.
Isn't like milliliters, like, I don't know if the exact number, but it's like something milliliters cubed.
Okay, so let's do this. So what I think that you're referencing is this thing right here. And right in the gut of our conversion chart, you've got a milliliter is a centimeter cubed, and that's a gram. But that's only if it's water, and this is a solution. So you're starting to bark up the right tree, just not quite there. Colton, go ahead. Say it again.
I was just saying, like on the lab, it was like 1 milliliter.
Exactly, precise. And again, that works for water, but if it's a solution, it doesn't work because there's stuff dissolved in here and it's heavier. So guys, what can we do? That's neat though that you remembered that lab conversion, Colton. Nice work. So guys, how can we get from milliliters to grams? So guys, let's do this. Ready? What unit are we in? What are we learning about? Well, moles, right? So guys, what we've eventually got to do is get to moles. Because if we can get to moles, it's a one-step conversion to grams. So we need a relationship between milliliters. Check this out. We need a relationship between milliliters and moles. We need a relationship between moles and volume. Moles and volume? What if we had a relationship between moles and volume? Have you ever heard of such a thing? A relationship between moles and liters? Come on, guys, pretend like you learned something 3 minutes ago. Moles and liters is molarity. So guys, that's the way that we solve this problem. We use molarity as a conversion factor. Now understand, right now we can't do that. But now we can, because now we're in liters. And now that we're in liters, we can get to moles. Because guys, if we don't, but if we had a liter of this solution, how many moles would be in here? Not 1, 0.1. See it? Guys, the molarity of this solution is 0.1 molar. So if we add 1 liter, we would have 0.1 moles of sodium hydroxide. And that's our next step. For every 1 liter, we have 0.100 moles of sodium hydroxide. Now guys, is it always 0.100 moles? No, but it is the molarity. And then guys, from there it's easy. We just need to go moles to grams, and we can do that all day long. Sodium weighs 23, oxygen 16, hydrogen's 1, add them up, you're out the door. But guys, that's the magic of molarity, is it becomes a conversion between volume and moles when we're dealing with solutions. Now guys, we just got to do the math. So we're going to go 225 divided by 1,000 times 0.1 times 40. And doing all of that math, I get 0.900225 grams. Now gang, I know that you're comfortable with significant digits, so let's do this. 225 is 3. 1,000 in a liter is perfect. The molarity is not perfect. That's 2 significant digits. And then guys, the mass off the periodic table is 4. So that leaves us with 3. So that rounded to 3 significant digits would be 0.900 grams. So we've dissolved 9/10 of a gram of sodium hydroxide in here. And we just made oven cleaner. Put it in a squirt bottle and off you go. So guys, now it's time for the hard pause. Let's think about what we've done. We learned about the concept of molarity. We learned how to make the concentration greater. We learned to make the concentration less. We learned to calculate molarity. And we just figured out how to use molarity as a conversion. So guys, anything there you want to talk about before we put molarity to rest, do empirical formulas really quick and then get on with homework. Go ahead. Great question. And in this problem, it will always be given to you. If it didn't tell you the molarity of the solution, you can't solve this problem. It has to be given. Go ahead, McKay.
Well, what would happen if it gave you like 0.25, like how moles?
Help me more with your question. I'm not tracking.
How would your work change if it gave you a different
So are you saying, like, for example, what if this was 0.250 molar? Oh, yeah. So the only difference with this would be 0.250. Everything goes. Yeah, so your first step in these problems is always milliliters to liters. Then at that point, it's liters to moles and then moles to mass. And again, the only difference would be if you started with liters. If it said how many grams of sodium hydroxide are contained in 3 liters of 0.1 molar, then you'd start in liters and you'd be here, and then it would just be 2 steps. What else, y'all? Are we good? All right. So guys, tuck this away, shifting gears radically, empirical formulas. We're going to define it. We're going to play with it conceptually for a minute. We're going to have an aha moment, and then we're going to do one calculation, which is exactly the same calculation that you're going to do in lab today or next time. And then, guys, we're done. This is like 5 minutes, and then you're going to get some homework done. So, guys, let me define empirical formulas. So, empirical formulas are the simplest formulas for a compound. And guys, again, this is what you're going to do in lab next time, is you're going to take a compound and you're going to stick it together. You're going to create. Create? Yes, create. You're going to create a compound, and by weighing the parts, you're going to figure out its simplest formula. You can also do this by ripping them apart, but we're going to put one together. You guys ready to go? Let's talk concepts. You're all caught up, right? All right, so guys, don't write this down. Just check this out. So what I want to do to help you understand this idea of simplest formula is, guys, share with you some chemical formulas that might be familiar to you. Please don't write these down, just check this out. So guys, some of you maybe have seen this chemical formula in biology class. Ribose, which is a sugar, is C5H10O5. Now guys, you may have probably, more likely, you've heard of glucose, right? Glucose is the sugar that we eat. It's plant sugar. It's the sugar that our body needs. It's the sugar we burn. And that's C6H12O6. Now guys, some of you are all too familiar with this next sugar because it makes you horribly sick. Your body does not contain the enzyme necessary to rip this sugar apart, and it gets in your stomach and then it bleeds into your small intestine and it doesn't belong there and it makes you really sick. Our good friend lactose. This is actually a sugar that cows make, and it's in cow's milk. And guys, there should be enzymes in your stomach that take this sugar and rip it apart so that when it enters into your small intestine, it's smaller. But if you don't have that enzyme, your body can't do that. And when lactose enters into your small intestine, it makes you crazy sick. Luckily, you can now take these little Lactaid tablets that contain that enzyme, and it breaks it down, and everything's good. Anyway, so guys, with all of that said, here's the question I have for you. What do all of these sugars have in common? Okay, so carbon, hydrogen, and oxygen. But guys, dig a little bit deeper. What else? They're all sugars, but guys, don't miss this. Go a little deeper than just carbon, hydrogen, and oxygen.
The carbon is double, so the hydrogen is double.
There you go. So the ratio is 1 to 2 to 1. So guys, the ratio for all sugars is 1 to 2 to 1, carbon to hydrogen to oxygen. Guys, this is the empirical formula for sugars. Do you now understand empirical formulas? But now guys, check this out. Ready? All sugars are part of a larger class of biologic compounds. Guys, carbon is carbo. And what is H2O? Water, which is hydrate. These are all carbohydrates. Guys, could that be our aha moment?
Yeah.
Come on. Guys, that's where the term carbohydrate comes from. All sugars and starches are carbohydrates, and the reason that we call them carbohydrates is because all of their empirical formulas can be simplified to carbon and water, CH2O, in a 1 to 2 to 1 ratio. Now guys, as you get further in biology, you're going to find examples where you're like, Knappenberger lied to me, it's not 1 to 2 to 1. Guys, when that's true, if you have a sugar and it's not 1 to 2 to 1, what's happened is this. Sugars are large chains of carbon, and sometimes they're so long that they'll actually bond together tip to tail. And when they bond together and they make what are called cyclic sugars, one water molecule is released. And when that happens, it throws off the 1 to 2 to 1 ratio because we lost a water. But other than that, all carbohydrates, all sugars are 1 to 2 to 1. You get the idea? Okay. So guys, the question then becomes, how do we know this? How do we calculate this? Let me give you the steps. Guys, in order to do this, it's a 4-step process. Step number 1 is if you are given percentages, use them as masses. That'll make more sense in a minute. Then guys, step 2, convert to moles. Step 3 is divide by the smallest number of moles. And step 4 is write the empirical formula. Now guys, in the lab as you're writing this down, in the lab that we're going to do on Thursday, you will not be given percentages, you will actually be measuring masses. But sometimes the data that you're given are percentages, and then we just pretend like they're masses, which works just fine. So guys, you'll solve a couple of these in homework, but then again, this is also what you're going to be doing in lab on Thursday. It's a good lab. All right, you guys ready? So here's the way this works. Imagine that you go into lab next time. This isn't the compound that we're going to do. But imagine that you go into lab next time and you weigh out some calcium and then you react it with some oxygen and some sulfur. And when that compound comes together, you figure this out. You don't need to write this down, but you do need room to solve it. So guys, we find out that a compound is about 33% calcium, 40% oxygen, about 27% sulfur. The question is this: what is its empirical formula? Guys, solve this with me now so that you have an example that you can draw on in the lab. So guys, this is the way we're going to solve these. We're going to take the percentages and we're going to use them as masses. But guys, when you do, set them up like this. Do these in columns and set them up for the one-step dimensional analysis process that's coming. So 33 grams of calcium, 40 grams of oxygen, 26.7 grams of sulfur. Now guys, I know that you're thinking, wait, these were percentages. They were, but we just changed them from percentages to grams, and we can safely do that. So 33.3 grams of calcium, 40 grams of oxygen, 26.7 grams of sulfur. So we just did step one. Use percentages as masses. Now guys, step two, and again, this is why we're doing this in this unit. These are moles conversions. So we just need to go convert to moles, and convert to moles. I did it all for you. Guys, when you do these calculations in homework in the lab, watch significant digits. 3 digits, 3 digits, 3, 3, 3, 3, 3, 3, 3. Watch your significant digits. Right off the periodic table. Yep, you got it, Alex. Yep. You ask good questions. Absolutely. So guys, we just did step two. We converted to moles. Please. Yeah, good question. And frankly, the answer is, let me turn off this so I can touch my board. Without it, sometimes the decimal place looks like a smudge. So I just put the 0 there so it's easier to find the decimal. It's completely unnecessary. I just find that from a distance, it's hard sometimes to find the decimal places. So it just makes them easier to find. Yeah, Sam.
So we wouldn't be wrong if we don't.
Oh, heavens no. No, it's completely non-significant. It doesn't change the... It's really a worthless 0, other than it makes finding the decimal easier. So guys, here's then what we know. We now know the ratio of these elements in the compound. It's about 8/10 calcium to 2.5 oxygen to 8/10 sulfur. Now here's the problem. You can't write a chemical formula from that because there's no such thing as a chemical formula. Let me start my board again and I'll show you. Guys, there is no such thing as a chemical formula that looks like this. You can't have Ca 0.83 O 2.5, S 0.83. That doesn't work. You can't have decimals in a chemical formula because you can't have fractions of an atom. So what we need to do is turn these into whole numbers. Guys, in order to turn these into whole numbers, that would be step number 3. Divide by the smallest number of moles. So guys, top, middle, or bottom, which of these numbers is smallest? Top, middle, or bottom? Top. So divide by it in all 3 steps. So now let's take a look at this. So guys, doing the math on the top, any number divided by itself is 1. Doing the math in the middle, 0.25 divided by 0.83 is so close to 3 that we're going to call it 3. Then guys, 0.832 divided by 8.30 to significant digits is 1. Now, guys, we've got whole numbers, and we can write the formula. We got 1 calcium, 3 oxygens, 1 sulfur, and that would be CaO2 O3S. Yeah.
Will it usually end up as 100?
Yeah. And the thing that's really, Kyle said, does it normally work out as whole numbers? And the answer is not only does it work out in our stuff, it will in lab as well. I don't know if you remember when we did that weird chart where we learned about Dalton and Rutherford and Millikan and Bohr and all those guys. That was actually Dalton's breakthrough. He called it the law of definite proportions, that when atoms bond together, they do it in whole number ratios. Yep. So guys, we're not quite done. Do this with me. Calcium is a metal, so is this a salt or a molecule? Calcium is a metal, which makes it a salt. Now guys, if the first thing were a non-metal, it would be a molecule and you're done. But guys, calcium is a metal, therefore this is a salt. So now let's name it. Guys, what would we name CaO3S? Well, you can't until you reorganize it. And then when you switch the sulfur and the oxygen, now what's this thing called? Calcium sulfite. So guys, if it is a salt, I'm going to ask that you write it in a way that you could then name. If it's a molecule, you're good. But if it's a salt, please rewrite it and make it into the actual formula of a salt. Okay, so guys, we are now all done. We are going, well, questions about empirical formulas, yeah. Sulfite. Sulfide would just be sulfur. Sulfite is SO3. All right, so guys, here we go. We are now doing homework assignment number 4. Here's what you're going to find. The first 4 problems, you're solving for molarity. The next 4 problems, you are using molarity as a conversion. And then, guys, the last 4 problems are empirical formula problems. We will grade these, we will review these on Thursday. But guys, again, please pause here for a minute. When I see you next, 3rd quarter's done. So guys, between now and Wednesday at 2:45, check Skyward. Make sure I haven't made any recording mistakes. If you're missing any homework from this unit or any lab work or activities from the quarter, guys, please get those turned into me before Wednesday at 2:45. So guys, we now have, less time than I thought. We still have like 12 minutes. So guys, the answers to the homework are up on the wall. The remainder of the day is yours. Please be in touch if you need. And let's see if we can get some stuff done.